So we ended on slide 19 or 20. It seems like it was 20 on the PowerPoint, but it's 19 on this once it comes up. It's like a textbook. Come on. All right, so this should have been the last slide that y'all saw. Okay? So we talked about the three different ways of separating a mixture. Okay? Does anybody remember the three types of mixture? The alloy is one. You guys got to talk up the mask on, I can't hear. A solution and a suspension. So which one's got the smallest particles? A solution. Which one's got the biggest particles? A suspension. And so I did this demo in class yesterday where I take some potassium iodide. Okay? And again, notice that the solution is always clear. Not necessarily colorless, but always clear. Okay? And so as a result, you know the particles are tiny in there. Now, this is the solution as well. It's clear blue. Now it's very concentrated, and so you can't see through it, but you can see that it's basically clear. There's no solid suspended in here. Solutions are always clear, not necessarily colorless, but always clear. But when I add some lead iodide, some lead nitrate, then I get this yellow precipitate. Notice now it's cloudy. That's an indication that it's a suspension now, that the particles are big and they're just kind of stirred up right now, but they will, you can filter these out. And you guys, we did that last year. We filtered out the precipitate on a stoichiometry lab. The ones I did yesterday, you can see they settle out due to gravity. They're sitting at the bottom. Okay? And so a suspension is the big particles, a solution is the small one, colloid somewhere in between. How can we tell the difference between a colloid and a suspension?
Shine a light.
Shine a light through it. What do we call that? The Tyndall effect. Okay? The Tyndall, Tyndall, Tyndall effect. And that's that's just, again, I talked about, and hopefully you understood, you know, when you go to the beach and shine the flashlight up in the air, you can see the beam. It's because of the dust particles in the air doing the Tyndall effect. Fog, when you had to have your low beams on because the water droplets in the air will scatter the light and just make this big white shield in front of you. Yet on a rainy night like tonight, if you're driving on a country road, it's going to be tough to see your headlights because there's no dust in the air. And so you're not going to see that beam at night because there's no dust to scatter it. Okay, so that's the Tyndall effect. Now, there were three ways that we talked about. So filtration, we all know about that. Now, we're going to do a thing called vacuum filtration this year. Well, ideally, we're going to do some vacuum filtration where we just, rather than letting gravity just pull it down, we actually create a suction and do vacuum filtration. But that's pretty obvious. Then this is the distillation apparatus right here. So when you're looking at this, this is my dirty water. This is just your mixture. And so you heat this up, and then you run cold water. And I had a massive flood this morning when I came in. Something was leaking somewhere. So it's coming down here, so it's leaking. It's leaking from right there. Anyway, so you heat this up, and now the cold water is running up here. So there's a tube inside this tube right here. This is called a condenser. And so the steam goes on the inside tube with the cold water running around the outside of the tube. That causes the steam to condense, and over here then you get pure water, because the impurities are usually ionic compounds that have much higher boiling points than the water does. So the water comes off, but all the impurities stay behind. So we get distilled water, which is really just pure water. Okay? And it's the same thing that they talk about with moonshine, with a still. You just kind of go in here. But the key point on this is that distillation is based upon differences in boiling points. Okay? Differences in boiling points. So if I have alcohol and water in here, if I'm trying to make moonshine, alcohol boils at around 79, 80 degrees Celsius. Water boils at 100. So you want to keep that temperature down, 78 to 80. So only the alcohol, mostly the alcohol is coming off, and most of the water and everything else is being left behind. And then instead of using something complex like this, they're out in the woods, they'll use a copper coil and just let it get air cooled. And so that as the alcohol goes through the coil and just cools back down, it'll condense back to room temperature and then drip into the jug for the moonshine. Okay, so distillation, this is a big thing. Just make sure you know it's separated due to differences in boiling points. And then lastly, chromatography. And here's just the example of chromatography that I had on the board, in that you put a dot, like a pen mark or whatever you're trying to separate here, and as the solvent, just by capillary action, the solvent's going to rise up that paper. Well, if the solvent is polar, what's the rule for solubility? What type of substance does polar dissolve? Polar. Light dissolves light. Remember that? Light dissolves light. Polar dissolves polar. Non-polar dissolves non-polar. So if this is a polar solvent, anything that's polar in your mix is going to want to stick with the solvent. So as the solvent rises up, the part that's polar is going to rise up with it. The non-polar doesn't attract the polar, so it's going to stay down here at the bottom. Now, if we reverse it and we put a non-polar solvent, then the non-polar part is going to go the highest up, and the polar would stay at the bottom. It's like dissolves like, so it's always going to go with it. So if whatever the solvent is, the part of the mixture that's like it is going to go the highest up. And then you get your RF factor, which is going to be the distance of the substance divided by the total distance that the solvent travels. Okay? And so if you have two different things, if you get the same RF factor for the two different mixtures, well, it's probably the same substance. Okay? That was kind of what I had on the board yesterday that you guys couldn't see very well. That and the three types of mixtures, but hopefully I talked enough about the three types of mixtures where you could kind of take notes off of, because that's not really on the PowerPoint. All right, so today we want to talk about numbers. Okay, this is where we do the dimensional analysis, our favorite thing, significant figures. Okay, the metric system versus the English system. I did this little quiz yesterday with the other class. Our English system, the United States was supposed to be completely converted to metric system by 1980. We're just a little bit behind. Okay, so let's just talk. Our English system that we refuse to change from. How many inches are in a foot? 12. Okay, that's easy. How many feet are in a yard? 3. Well, it really kind of depends on how many people are at your house, but typically we say 3. How many feet are in the yard? It's how many people. All right, I know it's early. Come on, you guys stay with me here, okay? All right, so 3 feet in the yard. So how many inches are in a yard? 36. Now notice none of those numbers have been the same, right? And then how many feet are in a mile? Yeah, I'm always amazed that you guys know that particular number. Some math teacher really works that into you or something, engineering or somewhere. So how many yards is that? That divided by 3. 1,760. Okay? Divided by 3, not multiplied by 3. Okay? right, so those are the ones that we're kind of familiar with. But how far is a fathom? Fathom is an English unit of measure. We didn't even heard it. 6 feet. Have you ever heard of Jules Verne's famous 20,000 Leagues Under the Sea science fiction book? Talking about a submarine before submarines were ever invented or created. Well, how far is the league? He went 20,000 leagues under the sea. I don't know, but it's a cool name for a book. A league is about 1.3 miles. Now, the key is that he didn't go 20,000 leagues down. He was just underwater and traveled 20,000 leagues under the sea in the submarine. Okay? So sometimes our brains just naturally 20,000 leagues under the sea, that's how deep he was. The reality is that's how far they went in the submarine around just under, they could only been like 6 feet under the water. Okay? So that's a league. All right, so that's length. Let's get into the fun one with volume. How many teaspoons are in a tablespoon? 3. Very good. Some of y'all you actually cook at home. Okay? How many tablespoons are in an ounce?
4.
I heard 2 and I heard 4. 2. Nobody's going to say 3? That's good because it's not. It's 2. 2 tablespoons make up an ounce. How many ounces make up a cup? 8. How many cups make up a pint?
2.
See, we don't know the system. You guys are all throwing it out there, but 2. How many quarts make a gallon?
4.
4, there we go, because quart comes from the word quarter, meaning 1/4. All right, now, if Peter Piper picked a peck of pickled peppers, how many pickled peppers did Peter Piper pick?
Peppers. And could Peter.
Okay, so listen to it carefully. If Peter Piper picked a peck of pickled peppers, how many pickled peppers did Peter Piper pick? A peck's worth, right? What the heck's a peck? What's a peck? Because the gallon doesn't start with P. A peck is actually 2 gallons. Okay? Now, here's the problem, that you can't really pick a pickled pepper. That Peter Piper would have to pick a pepper, then pickle it. Okay? I say that pretty easily, and you guys should try to say that. That's kind of hard to say.
It's hard to say.
I've had years of practice, okay? So a peck is an English unit of volume, 2 gallons. This little light of mine, I'm going to let it shine. Hide it under a bushel? No, I'm going to let it shine. What's a bushel? If you look on the stock market, corn and soybeans and apples and all the veggies, everything's sold at price per bushel. What's a bushel? Have you ever been to like an outdoor market where you see the wicker baskets with the apples or the oranges or something in there? That's a bushel. It's 8 gallons. Okay? It's 8 gallons worth, for volume size wise of what you can put in that bushel. English units. We don't even know it. Okay? Oh, I forgot a length one. In the Old Testament, the Bible, God told Noah to build an ark so many cubits by so many cubits by so many cubits. What's a cubit?
30 feet.
Nope. That's a yard.
Oh, yeah.
A cubit was the distance from the king's elbow to the tip of his fingertip, and that was 18 inches. Now, if the king had short arms, it would vary, but we've now established it to be 18 inches is a cubit. Okay? A foot was the average size of a soldier's foot. Okay, but that varied too, but they finally made it 12 inches. All right, so the English system is a pain. Okay, back in the 70s or 80s, I think it was in the late 70s, they were sending one of the first unmanned vehicles to Mars. But there were 2 different companies, one in Florida, one in Colorado, that were working on different parts of the project. And when the thing took 2 years to get to Mars, when it got there, it crashed into the surface of Mars and was destroyed. Because the company in Florida used the English system, the company in Colorado used the metric system for thrust, and they didn't match up right, and they didn't have enough, thrusters to slow it down when it was coming to the surface, and it crashed, and it was a $25 billion football because of the difference between English and metric. Okay? We all need to be on the same page. I'm on a mission from God to get the United States to convert to the metric system. It's so much easier. Okay? Now, in the metric system, you're only going to need to know a few of the actual quantities. So if we look, this is on page 16 of your textbook. Okay? These are all your prefixes. Okay? You don't need to know all of these. Okay? Because we don't use most of them. But we do use kilo, deci, centi, milli, micro, and now with computers, nano, and even getting into picoseconds as far as how long it takes to process. Okay? But if you just learn these exponents, all that means is the number doesn't change, we just move the decimal point. And if you can learn the exponents and the difference between the exponents, we can so if I want to go with 150, I'll say centimeters, is equal to how many kilometers? Okay, not sure why you would need to know that, but let's just say we need to know that. Well, centimeters is what exponent? 10 to the negative 2. In other words, 1/100th of a meter. There's 100 centimeters in a meter. Kilo is what exponent? 10 to the third. So I know between negative 2 and 3, what's the difference in the power of 10? 5. So I'm going to move it 5 places. Now, if you want to know, you always go -2 minus a positive 3, and that's going to equal a negative 5. So the negative means that I'm going to move it to the left. I'm going to make it smaller. If it comes out positive, I'm going to make it bigger. Okay? So the metric system, unlike 12 inches, 3 feet, 5,280, where the number changes every time, in the metric system, you just move the decimal. It's so much easier. It makes so much more sense. Okay? So you're going to be responsible to know these all the way to nano. Just this section right here. All the other ones, now it's nice to know mega's a million, giga, from Back to the Future, so many gigawatts, actually now though, when you talk about hard drives, aren't they into the terabit? Yeah. Okay, so that's what they're talking about here, 10 to the 12. Okay? Because it used to be, when I started, it was kilos of memory. Then we went, oh, mega, that's huge. We got these huge hard drives. Then giga, and now they're already the tera. Okay? So, if we just want to convert, just move the decimal. You need to be able to do that. Okay? And we're going to practice converting between English and metric as well. That's kind of what some of the worksheet that's due for tomorrow is about. Okay? All right, so let's go back. All right, so we're going to look at all these different things. All right, in the metric system, there are 7 base units. Okay, we're in what's called the MKS system, meters, kilograms, seconds. So when you want to put anything into, and this is really more important in physics than it is in chemistry, but if you put anything into an equation like F equals ma, okay, or kinetic energy is equal to 1/2 mv squared. Anytime you have an equation like that, the mass has to be in kilograms, the length has to be in meters, time has to be in seconds. The metric unit of temperature is the Kelvin. How do we convert Celsius to Kelvin? It's 273, so it's Celsius plus 273 is is equal to Kelvin. Okay, so 0 degrees Celsius is 273 K, 100 degrees Celsius is 373 K. All right, so we need to know that. Okay, mole, we've talked about the mole. Okay, now at the very end of the year when we do electrochemistry, we'll deal with amps, which is really a coulomb amount of charge per second, coulombs per second, and we'll learn more about that. And we won't ever use this one, luminous intensity, but a lot of times they'll talk about how many candles, the brightness of something. Sometimes light bulbs now, the LEDs are putting the how many candles, they are, the intensity of the light, okay? And so these three, MKS, meters, kilograms, seconds, okay? Those are the base fundamental units. So it's not the gram, it's the kilogram. Is the fundamental unit for the metric system. Whenever you plug it into an equation. So an F equals ma, you've all heard that equation, right? Because of Newton's second law. Mass would have to be in kilograms, acceleration would be meters per second squared. And then that would give you a Newton, would be the derived unit of kilograms meters per second squared, we call it Newton. So if you don't put the right units, then it's not going to work out right. All right, so that's just kind of going through there. Now, one point on this is that a cubic centimeter is a cc or a cm cubed. So when they hear on the doctor shows, give them 10 cc's of adrenaline stat, that means a cubic centimeter. That's the equivalent of 1 milliliter. So you need to know that a cubic centimeter, I use this one, a cubic centimeter is going to be the same as a milliliter. 1 cubic centimeter equals 1 milliliter. So that way you can interconvert and just make, sometimes we need that for conversion factors. Okay, so that's all that's in the book right there. Okay? And that's, so I don't even need to go over that. You can just look at that. Volume, okay? And here is where it says it's 1 centimeter by 1 centimeter by 1 centimeter. So this is the point here that's making a milliliter and a centimeter the same. Okay? By the way, this is not my PowerPoint. This is the book PowerPoint, so I don't really have it memorized or whatever, so I'm just kind of going through it. But these are the different things in there. But this is all pretty basic stuff. All right, so here are your 3 temperature scales. There's actually a 4th one. So just imagine there's another scale, another one that looks just like this. Okay? Notice, does anybody know what the Fahrenheit scale is based upon? I didn't hear what you said.
Like how you feel?
You have to speak up. I'm old, y'all. You have masks on.
Oh, like how you feel, you know?
How you feel? Okay, well, it is kind of based on the human body. Okay? Daniel Fahrenheit used the freezing point of salt water. If you add salt, we know that when we made ice cream last year, you put the salt in, and I guess it's like we didn't do it because we didn't have an end to the year. But you put salt in your ice cream maker, and that lowers the freezing temperature. So when you have a saturated solution, in other words, you put as much salt as you can possibly put into the water, you've lowered the freezing point, the maximum amount. Fahrenheit put that at 0 degrees. Okay? Then he used body temperature as 100. Now, I don't know if because he was out in the German winter, if he had a slight fever, okay? Because what's average body temperature now? 98.6. Now, mine is never 98.6. I don't know if you've ever been to the doctor. Nowadays, they take temperature everywhere, okay? My normal is somewhere around 97.5, 97.4, somewhere in that range. I'm a little more cold-blooded, okay? But he put 100 as his body temperature, okay? Now, we now know it's 98.6, but he marked it at 100 and then just did the divisions between 100 and 0. And at that point, pure water freezes at 32. Okay? Water boils at 212 on that scale. No real rhyme or reason, but there's 180 divisions between the freezing and boiling point of water. Now, a Celsius scale, the mercury or the alcohol, if it's silver, it's mercury in the thermometer. If it's red, it's alcohol in the thermometer. it's gonna rise and fall the same way, no matter what scale you have on the glass tube. So Anders Celsius went and said, well, let's just make freezing point of water 0 and the boiling point of water 100. And then divide that up. It's a lot easier to measure and it's a lot more accurate. But there's only 100 divisions between the two. So which one is actually a smaller division? Fahrenheit or Celsius? Fahrenheit is, there's 180 divisions here. There's only 100 divisions here. So 180 over 100, y'all have seen the conversion factor 9/5 times whatever. That's the 180 over 100 is the difference between the number of divisions between, on the Fahrenheit scale, between water's freezing point, boiling point, and that on the Celsius scale. That's where the 5/9 or 9/5 all comes in, is that difference between 180 and 100. Now on the Kelvin scale, the only thing that's different is where 0 is. What's 0 in Kelvin? Absolute 0. What happens at absolute 0? Everything stops moving. Just you heat them up, speed them up, cool them down, slow them down. When you get to absolute 0, all the vibratory motion just stops. Now, theoretically, it's impossible to reach. But I talked yesterday about Bose-Einstein condensate to where they go within millions of a degree. But it's theoretically impossible to get to absolute 0. Because in order to get to 0, you have to have something below 0 for the heat to flow into. But if 0 is the bottom, there's nothing for it to flow into, so you can't quite get to the bottom. You always have to have a heat sink, but if, once you get to the very, very bottom, you can't get to that. Okay? So this is actually the Kelvin scale, but how many divisions are there between the freezing point and boiling point of water? So what does that mean about the change of a degree Kelvin and a change of a degree Celsius? They're the same. So in an equation, if it has delta T, we talked about specific heat, Q equals MC delta T. If it's a change in temperature, it doesn't matter whether it's Celsius or Kelvin. You don't have to change it, okay? Because the change in temperature between the two is going to be the same. However, if it's just T, PV equals nRT, the ideal gas law. If it's just T, it has to be in Kelvin, because that's the metric unit. Okay? Now there is an absolute scale for the Fahrenheit, and it's called the Rankine scale, R-A-N-K-I-N-E. Now this is just strictly my information, because nobody in the world uses it, okay? Because nobody uses Fahrenheit except us, okay? The Rankine scale, so again, they make absolute 0, 0, and that's negative 459.54 degrees Fahrenheit. Okay, so just like Celsius, you would add 273, you add 459.54 to Fahrenheit, and you get the Rankine scale. But it's the equivalent of the Kelvin scale on the Fahrenheit. Okay? I was just going to say something, I forgot. Okay? So, temperature is measured how hot or cold. It's really a measure of the average kinetic energy. What does kinetic energy measure? Anybody have physics yet or engineering? You should know. Kinetic energy is energy of motion. It's how fast things are moving. Okay? Temperature is a measure of the average kinetic energy. You heat them up, the average speed increases. Cool it down, the average speed decreases. And so it's a measure of hotness or coldness, but if you put an ice cube into your hand is a higher temperature than the ice cube, so your hand is hot, the ice cube is cold. But if you take your hand and put it on a hot skillet, the skillet is hot and your hand is cold. So it's all temperature determines the hotness or coldness of something. Higher temperature is hot, lower temperature is cold. Heat always flows from hot to cold. There really is no such thing as cold. How do I make this room dark? Turn off the lights. Is there a dark switch that I can turn on? The only way to make the room dark is to block all the light, remove all the light. So darkness is simply the absence of light. It's not really a thing. It's just the absence of something. Cold is the exact same thing. Cold is the absence of heat. You can't put cold into something, you can only take heat out of something. So this air conditioner right here is taking the hot air, and then there's some cold coils on the other side of that wall, and the hot air is being blown over those cold coils. The heat is transferring from hot to cold, going into the cold coils, okay? And then the air that comes out now has less heat in it, and so we call it cool or air-conditioned air. But now those coils get hot, so then they have to pump it over there by the gym to those big coolers over there. And then they have to cool the water down again and send it back. So the heat is actually going from the room to the water in the coils to then over here and then out to the atmosphere. So we're moving the heat from this room down by, you know what I'm talking about, down by the gym, those two big, real aluminum, silvery looking things that are outside the cafeteria. That's what's cooling us and making us comfortable. All right, heat always flows from hot to cold. All right, this is, we've already talked all about that, Kelvin's 273, okay? So here's your conversion. You will never have to do this conversion, okay? But that's where the 9/5 and 5/9 come in, is the 180 versus 100. All right, density is something very important, okay? It's mass over volume. Now, again here, in density, you can use any mass, any volume. Any mass, any volume. It doesn't have to be MKS. Usually we use, for solids and liquids, use grams per milliliter or grams per cubic centimeter. And for gases, grams per liter. Okay? So you might want to write that in there. For solids and liquids, it's grams per milliliter. For gases, it's grams per liter, because gases are so much more spread out, the density is so less. If you use grams per milliliter with a gas, the number's going to be real tiny. Okay, and we'll do some conversions with that. And one of our first labs is calculating the density. I don't know how we're going to do that. All right, exact and inexact numbers. We're going to talk about sig figs here, okay? Different measuring devices have different uses, and you got to realize in chemistry, every number is a measurement. So we have some kind of measuring device. Now, you know that if you have your weight on a bathroom scale, I would always give it plus or minus 2 or 3 pounds as far as accuracy is concerned. But if I go in here with our electronic scales, they're going to be much more accurate. They're going to have a whole lot more certainty in the measurement. So we always want to go and use the maximum amount of accuracy, certainty, the maximum number of significant figures without exceeding the limits of the measuring device. Okay, so bathroom scale, we can't say our weight on to 4 or 5 decimal points on a bathroom scale. Mine goes to 1 decimal point, that's a digital, but even then it fluctuates and it's going to be different, you know, if I step on it 3 different times. Okay, so it all depends upon what measuring device you're using. And just for the record, a beaker is the worst way to measure volume. And we're going to go through and learn different ways, different pieces of equipment that are more accurate than others, measuring volume. Okay? Pipette, these are just different measuring devices. All right? We've probably heard this one. I'm working on getting to sig figs here, but accuracy versus precision. So on the dartboard, accuracy is how close you are to the right answer, the bullseye. Precision is how close your answers are to one another. You can be very precise, but very inaccurate. That generally means that there's some built-in error. You're doing the same thing wrong over and over and over again. Maybe the balance is off and it's not calibrated right. Maybe, you misread the directions. You put in 10 milliliters instead of 1 milliliter or something. Okay? But you're doing the same thing over and over. Ideally, you want to be precise and accurate. We don't really want this. However, if you have something like this, you can actually, poor accuracy, but you're going to take the average of those 3, And if you're far enough apart, the average is gonna come out pretty close to the right answer. So we'll always do multiple trials so we can get a variety of values and then take the average of those, because that helps narrow it down to what the real answer is. Okay? Now, percent error, you need to know this formula. Does anybody remember?
Measured minus actual.
Okay, so I'll use that. I measured, I usually say experimental. And EXP apostrophe T, that's my abbreviation always for experiment, or any form of the word experiment, experimental. The measured value minus the actual value. This is the correct answer. Okay? Divided by the actual. You don't care. You don't want to divide it by your value because your value is what you don't know if it's close or not. You want to compare it to, well, how close am I to the actual value? And then times 100 to put it into percent. Okay? So this gives you the error. This gives you the percent error. And when we come back from the break, we'll talk about that. Zoe, will you hit pause on that? Now, precision is measured by deviation. The only difference between error and deviation is instead of using the actual value here, you're going to use the mean value, which, what does that mean, the mean value? Average. The average. Because you don't care what the right answer is, you're just comparing how close are your answers to one another. Okay? So you just substitute in the mean value for the actual. Now, you will never have to calculate deviation. But deviation measures precision. And so that's where, like when you take the ACT, that gives you how many standard deviations you are away and what percentile ranking. And that's all based upon what everybody else did, not necessarily how, the raw score that you did. So that's a measure of your precision. How close, were you to the average? Were you way above the average? Were you way below the average? Were you right at the average? And so that's a deviation. So when it talks about your percentile ranking, okay? We're not going to have to do that. All right, this is the fun one. What does significant figures mean? What's the whole point of significant figures? What? I mean, why do we have to learn significant figures in the first place?
Make things simpler.
Well, that doesn't really make things simpler. We just hate them. Okay? But what's the whole point? See, if you can understand the point of significant figures, then it makes more sense.
To be consistent.
To be consistent, it's a system of rounding to know how many decimal places we ought to use in our answer. But more importantly than that, it's a system that allows us the greatest degree of accuracy, the greatest number of decimal points, without exceeding the limits of what we use to measure the data that we got. So if you're doing density as mass divided by volume, but the mass you have on an analytical balance to 4 decimal places, but the volume you just measure in a beaker, there's something else going? All right. Okay? If you measure the volume in a beaker, the beaker is only going to be maybe good to the ones place, not even any decimals, and really it's only plus or minus, it's like 5% active. There's plus or minus 5%. So really it might even be the tens place as far as the accuracy is concerned. So you can't go, when you go mass divided by volume, you can't go out to 5, 6, 7 decimal places, even though that's what shows on your calculator. because your measuring device did not measure it that accurately. The significant figures gives us, well, how accurate can I report my answer to them based upon what I use to measure any piece of data that's used in the calculation. Okay, so significant figures are all the ones we know for sure, plus one digit of uncertainty. In other words, there's some guesstimation, some rounding in that last digit. So if I look at a graduated cylinder, or let's just say a burette, okay? Okay, so let's just say that this is starting at 0, and this is 10. This is 10, okay? If I put the meniscus right there, what do we say the volume is? 6, okay? But I can always go, everything I know for sure, I know 1, 2, this is in the ones place, I know it for sure, and then I can guesstimate, well, it's right on the line, so I'm gonna say that this is 6.0. One past whatever the smallest division is. One digit of uncertainty. Now, if I take and measure something else, and it goes to there. Okay, now there's some guesstimation, right?
Yeah.
So you're gonna say 7.1, 7.2, 7.3, you guys all might have different values there. We try to guesstimate, break this up into a scale 1 through 10. So I would say that this is 7.2. But I'm not gonna be able to say this is 7.2 and then just say this is 6. Because if this measures to a decimal point, that measures to a decimal point. This is all gonna measure to one decimal place. Y'all with me on that? So that's why we have to be consistent in our measuring, and it's always gonna be one past whatever the smallest unit is. So if this happened to be 0 and 1, okay, then that's going to end up being 0.60 and 0.72. Now we get 2 decimal places out of it. Because the smallest unit is in a tenth, which means we can go to the 100. Always one past whatever the smallest unit is. So when you're measuring, that's the whole point of sig figs, is getting as accurate as we can without exceeding the limits. And the rules say everything we know for sure plus one digit of uncertainty. Now, if it's a balance, a digital balance, whatever the balance says, you don't just add a digit onto the balance. Whatever the digital says, you do it. It's just when you're reading a graduated something like a ruler or a graduated cylinder or a pipette, anything that's got lines on it, you're going to always go one pass. So it's all about being as accurate as possible, okay? The problem is that zeros, non-zero digits always show accuracy. But non-zero digits have 2 different functions. I went to a concert. There are 10,000 people there. Do you really expect there to be exactly 10,000 people? Could I just say there was one person there? What's the function of those zeros? Placeholders. They just show me what place does the 1 need to be in, give me an order of magnitude. How big is that number? The same thing is if I go and measure the mass of an ant. It's 0.00035 grams. Okay? Those zeros at the beginning are telling me how small the number is, just like the zeros at the end of 10,000 tell me how big the number is. They're just placeholders. So zeros at the end of a big number with an understood decimal, in other words, the decimal point's not written, are just placeholders. So they're not showing accuracy, so we don't call them significant figures. They're important, gotta have them, but they're not significant. They don't show accuracy. However, if we have something like 15.0, Does that zero change how big or small the number is? What's the point of putting that zero? To show we measured to that degree of accuracy, right? That my balance or whatever I'm measuring goes to one decimal. And so the same thing is true if I said 0.005200. These zeros are showing the placeholders, but these zeros, you wouldn't put them unless they were showing accuracy, unless you could measure out to that degree. So these are not significant. And this is always just going to be sig figs, SF. These are significant. The non-zeros are always, they're never a placeholder. Zeros are just tough because they're placeholders. So all you need to do is memorize 2 times. At the end of a big number, at the beginning of a decimal. Those are placeholders. Everything else counts. Okay? And it's just which ones show accuracy versus which ones are just placeholders. And zeros are the only thing that's confusing on that. So if I give you, just see if by chance, I don't know what the next slide is. I hope it. No. Okay, so if I give you, obviously, if I said 1, 2, 3, 4, that's going to be how many sig figs? 4 sig figs. Okay? But if I said 1,200, that's just going to be 2 sig figs, because those zeros are not there. But if I say 1,200 and I write the decimal point, now that's saying those zeros are showing accuracy, that there were exactly 1,200 people, or it weighed exactly 1,200, or I had exactly 1,200 anything, that I was measuring. So this is going to be 4 sig figs. Okay? So if I say 0.02050, the last 4, right? Is everybody good with this?
Yeah.
Okay? I don't want to just keep harping on it if we understand it, but sig figs give people a issue. Now, here's the good news about sig figs. On the AP test at the end of the year, the maximum number of points that you can lose on the free response on your answers is 1 point for sig figs on the whole test. Not 1 point per problem, 1 point on the whole exam. So it's not a big deal. We still want to do it right and understand it because it's an important concept in science. But we're not going to stress over it because it's not a major point on the AP test. Okay? Now, when we're adding and subtracting and multiplying and dividing, we have different rules. But you all have heard the expression, you're only as strong as your weakest link. So, if I'm going to go with 25, that wasn't anything. Okay, plus 1.5, and then plus, go down here, 160.247. I want to add all those 3 numbers up. Okay? Well, I'm going to get 7, 6, 7, 6, 8, 186.767. But I'm only as good as my worst answer. Remember, sig figs are all the ones we know for sure plus 1 digit of uncertainty. So this digit has uncertainty, this has uncertainty, that has uncertainty. Which means there's uncertainty in all 3. We're only allowed everything that we know for sure plus 1 digit of uncertainty. Whatever is my weakest, lousiest value, that's how many decimal places I can have. I can only have, this has 2, this is 1, this is 3. I'm only as good as my weakest link. So I can only have 1 decimal point. So what would that round to? 0.8. Addition and subtraction, it's all about the position of the decimal point. How many decimal places do you have? And that goes true even if you go into the 1's place, 10's place, 100's place. Whichever is your least accurate value, That's the best you can do on your answer on addition and subtraction. Now multiplication and division, 25.02 times 1.7, okay? Now it's not gonna matter as far as decimal points. Now it's gonna be 4 sig figs times 2 sig figs. So how many should my answer have? Your answer is gonna have 2 sig figs. So if I went 25.02 times 1.7, I'm gonna get 42.534. Okay, because that's what's going to show my calculator. But sig figs tells us where do I need to round it off to? Okay, only 2 decimal places, so it's just going to be 43. So that's the most accurate I can report my answer. That's the point of sig figs. Because your calculator is going to give you all these decimal points. Okay? You're only as good as your weakest link. There's a life lesson in that. You can work your whole life of developing a great reputation. It only takes one screw up to really kind of mess that up. Your reputation, your integrity is only as good as your worst screw up. Now, luckily in life, we get do-overs and we get second chances and we can make amends. But when you're out on a Friday night, you got to remember that bad decision is going to go with you a long time. Doesn't matter how good you were up to that point. They're going to remember the bad decision. The integrity is only as good as your worst screw up. But thank God for God and God is gracious. All right. Now, dimensional analysis we'll come back to. I think that's it. Let's look at the worksheet then that is assigned to you. Okay? If you need to pull out your phone or your Chromebook, I'm going to put it up here as well. Hopefully I can get it in classroom. Okay, so now we want to talk about dimensional analysis, which is just units. So just super quickly, and then I'm going to let you use the rest of the time to work on this. So I have 0.0569 moles, and it wants to know how many atoms. Well, what's my conversion factor between moles and atoms? So I'm going to always start with what's given, 0.0569 moles. Now, I don't know, different teachers do different things. I just use a parenthesis, like in math, but some teachers do what we call kind of the railroad track method, where you have the top and bottom. Did Miss Guthrie, anybody have Miss Guthrie? Did she do this or she do parentheses? She just kind of did time, didn't she?
Yeah.
Yeah. Okay, but we know that a parenthesis next to something is going to be a times. Okay, so you'll see sometimes written like this. Okay. So where does moles need to go? So I'm going to say 6.02 times 10 to the 23rd atoms in 1 mole. Moles cancel. I'm left with the unit that I'm looking for, so I'm just going to multiply these 2 numbers together. Now, how many sig figs is this? 3. How many sig figs is this? No, it's not exact. It really goes 6.022. It goes on out to a whole bunch. So you're going to have 3. It's only given the 3 sig figs here. And again, with scientific notation, it's only these front numbers. These are all your placeholder zeros, the 10 to the 23rd. That shows my order of magnitude. Okay? So what does that come out to? Somebody to 3 sig figs. Go ahead, Esther.
3.43 times 10 to the 22nd.
Okay, so here's a point. Number one, I strongly, with everything in me, with all of this grayness, wisdom, experience of teaching kids for 39 years, put the units on your conversion factors. Units tell you whether or not to multiply or divide. They tell you what to do next. Units are your friend. Use the units. And if you want to get credit for your answer, you must have, we're going to talk about proper sig figs, but you must have a unit on it. Atoms, moles, grams. Because just saying 3.43 times 10 to the 22nd, what? You need to always label your answer. Every answer that we do in here will have a label of some kind. And it's whatever's last up here. Okay? Now, let's drop down to number 5. Okay? 698 miles per hour. First thing you need to understand, that this miles per hour translates to this. It's not miles per hour over 1. It's miles over 1 hour. There's an understood 1 hour there. Okay? So make sure that, so when you're setting your units up. Now, what's going to happen is we're going to go to kilometers per day. I have two conversions that I have to do in one problem. Okay? Now, 698 miles per 1 hour. So I'm just going to take miles to kilometers. What's the conversion factor between miles and kilometers? 1.6, what is that? Just 1.6 kilometers over 1 mile. Miles cancel. So if I stop right there, what's my unit? Kilometers per hour. Okay? So just so you know, that if you ever want to know your kilometers per hour, it's always times 1.6. So if you're going 100 miles an hour, you're going 160 kilometers per hour. Okay, so it's an easy conversion if you ever. Now, most of our speedometers have both of them on there now because, well, everybody in the world uses metric system except us. But so they want to sell the car anywhere else. Okay, now I got to take hours to days. Well, how many hours are in a day? 24. But since hours is in the bottom, I know hours need to go on the top over 1 day. Okay? Now, how many sig figs do I have here? 3 sig figs. How many do I have here? 2 sig figs. What about this one?
24.3.
No, I think it's 24 hours. Well, is it because that's how we get to 365.25? But most people, we're going to count this as an exact number, which means it really has infinite numbers of sig figs. So we don't count that in our sig figs. So if you have like 100 centimeters in 1 meter, that's by definition exact. 12 inches is 1 foot. That's an exact measurement. That's infinite numbers of sig figs. So you don't count those into your sig fig calculations. Okay? Also, you don't, the ones, you always assume that it's 698 miles per exactly 1 hour. There's approximately 1.6 kilometers in exactly 1 mile. There's 24 hours in 1 exact day. Okay, so you don't count the 1. So we want to multiply all of this out, and it's going to come out to how many sig figs? 2. So somebody give me what's the answer when you multiply it all out without rounding?
168 over 1 day.
168 comes out to that exactly?
268.
268. Okay, and that's going to be kilometers over 1 day. Okay, but how many sig figs? What will we round this to? But how many sig figs should we have in our answer?
2.
Only 2. So what does that round to 2 sig figs? 270.
Should be 270 pounds.
Yeah.
To what?
It should be 27.
Or 27 pounds.
Okay, so, that's true, because we can't be smaller than 698, so it's 268,000,
Yeah.
okay?
Or, no, 26,800.
We'll get there, 26,800 kilometers, so then that goes to 27,000 kilometers per day. Okay, so when we have multiple, you just do the two. Now, you can just do it all in one step. Sometimes it's gonna be 4, 5, 6 parentheses long, but whatever's on top here, we know has to go on the bottom here, unless of course kilometers is what we're looking for. So miles, okay, I need to make my units cancel. That's your dimensional analysis, okay? I wanna do one more. I don't see any on there like this. But the density of gold is equal to 19.3 grams for every 1 cubic centimeter. Okay? So a cubic centimeter, a little tiny box of gold is going to weigh 19.3 grams. I want to know how many pounds per cubic foot that's going to be. So if I have a foot by foot by foot block of gold, how much is it going to weigh? Okay? So I'm going to start 19.3 grams over 1 cubic centimeter. What do I need to do next? Do I have anything grams to pounds?
We have pounds to kilograms.
I have pounds to kilograms, right? So I got to get my grams to kilograms. So how many grams in a kilogram? 1,000. Okay, I want to put grams on the bottom, so I'm going to say 1 kilogram over 1,000 grams. Now that's by definition, so we call that an exact number. Okay? So now I have kilograms. So now I can go 2.2 pounds over 1 kilogram. So if I stop right there, that's pounds per cubic centimeter. But I need pounds per cubic foot. So I don't have a centimeters to foot, but what's my conversion factor with centimeters in? 2.54 centimeters is an inch. But I need cubic centimeters and cubic inches. So if I look at a cube, I can never draw you. Okay? I'm going to be 1 centimeter by 1 centimeter by 1 centimeter. Okay? Or let's just say 1 inch by 1 inch by 1 inch. Sorry. Well, for centimeters, that's 2.54 times 2.54 times 2.54. Right? So to get cubic centimeters versus cubic inches, I need to cube this. Because that's going to get me cubic centimeters over a cubic inch. So when you need a square or a cube conversion factor, just use the linear one and then raise it to whatever power you need. So now how many feet or how many inches are in a foot? 12. But again, now I need cubic inches and cubic feet. So I'm going to cube that. Okay? This is an exact number again. This is 3 sig figs. This is 2 sig figs. This is 3 sig figs. You count the given as well. So how many sig figs should we have in our answer? 2. So it's 19.3 divided by 1,000 times 2.2 times 2.54 cubed times 12 cubed. Somebody, anybody? I'd like, you already have that? Do you have an answer?
I did not calculate.
Okay. Oh, that's true. This one's not on the sheet, so this is made up one. So we've got to plug this in. working on it, Anastasia's working on it. We need to have two people agree on an answer.
1,202.333306. I got this in
Okay? So this is how many pounds per cubic foot. But if I round that off to 2 sig figs,
Just 12.
I have it written right? You said 1,202. Okay? So what's this going to be to 2 sig figs? Just 1,200. Okay? So in other words, a 1 foot by 1 foot by 1 foot gold brick is going to weigh 1,200 pounds. So when you see them in the movies with these gold bricks that are like this, they're just throwing, 20, 30 of them into a bag or of some kind and carrying them out. It's not going to happen. Each of those bricks is going to be weighing 300 to 400 pounds. I mean, they're just going to be super heavy. They're not going to be, it's just, I always get amazed at those things. All right, so, there's only a few minutes left. Work on this. You have all tomorrow to work on it as well. Let's do it midnight tomorrow night. Okay? Practice with your sig figs. Practice with your dimensional analysis using units, squares, and cubes. Okay? Start with what's given. Find the appropriate conversion factor or factors, and then set your units up so they cancel. That'll get you the answer every time. I have a handwritten letter over there from one of my first students. Way back when I actually had dinner with her last summer, and she lives in Seattle and is married. You've been teaching a long time when your previous student is 52 years old. Yeah, 3 grown kids, married, all that stuff. But she wrote me. When she left the high school I was teaching at and went to nursing school at the University of University of Carolina. Let me see. Yeah, it was North Carolina. What's North Carolina called? The University of North Carolina? Is it University of North Carolina? Anyway, she went there to nursing school, and she was in the middle of doing something that really wasn't a chemistry problem. But she wrote me a long letter and just said, "Ms. Howe, I just want to thank you. I was sitting in my dorm and just trying to figure out how to do this problem, and your voice came into my head. Start with what's given, find the appropriate conversion factor, set your units up, and I was able to solve the problem." Okay? And she got such a rush that she felt the need to write me a handwritten letter. We didn't have email back then. And it just makes a big difference. You can use this method for the rest of your life in every kind of math, science, business class you ever take. It'll work. All right. By the way, just so you know, we're going to do chapter 1 and 2 together, and then take a test over chapter 1 and 2. This stuff's all pretty straightforward, pretty easy. All right. You can hit stop.